Hello everyone. In this video we look at the first of the metal extraction steps, which is enriching of the ore. It's also called as concentrating the ore or even sometimes dressing of the ore. So what is this enriching of the ore basically? It is a step where we will try to get rid of the unwanted earthy particles, whether it is the particles of sand, gravel, or even some of the other chemical substances. Sometimes we will be able to remove them from the ore and concentrate the ore, so to say, so that we can proceed on to the further steps of the metal extraction process. So we have a couple of standard methods that have been deployed in the metallurgical industry, and some of them are quite historical in the sense they have been used over the years, and some of them are little bit modern in terms of their usage. So we'll take a look at what are these metal enriching steps. But basically this is a step where we'll remove the gangue particles and concentrate the ore. Okay, and the commonly followed four methods for this are levigation, which is also called as gravity separation and even called as hydraulic washing. The second method, which is used mainly in the case of sulfide ores, is froth flotation, and the third one is electromagnetic separation or even sometimes called as magnetic separation. This is mainly useful for the separation of substances which have magnetic properties. And the fourth, which is used in especially the case of the noble metals, is the chemical method called as leaching. Now, beginning with the levigation, it's one of the very old metal enriching methods, or the ore enriching methods, where the ore that is mined out of the earth is put into a stream of water or current of water. The heavy ore particles will settle at the bed of the river current or the water current, whereas the lighter particles will get carried away by the water flow. And since most of these mining places will have a water body close to them, traditionally the ores used to get enriched in this method. But considering the environmental impacts of this particular process, of late there have been changes in terms of the way this process is being deployed, and we do use it for oxide ores and carbonate ores. And here the fact that is helping us to separate the ore particles from the gangue particles is the density difference between the ore particles and the impurities. So here, if you look at, in most of the cases, oxide or carbonate ores, the ore particles will be the heavier ones and the gangue particles will be the lighter, so that they can get carried away by the river flow or the water flow. So this is the levigation or the gravity separation. It's also called as hydraulic washing. The second method that is mainly used in the case of sulfide ores is froth flotation. Froth flotation is based on the idea that if we have two kinds of solvents, one is able to wet the ore particles better and the other is able to wet the gangue particles or the impurity particles, then we will be able to separate them or segregate them. So this is based on the concept of what we call as adsorption phenomena. So where the particles of one will be able to adsorb on the surface of the other type of particles. So we'll take a look at what this process is. We'll have feed from which we'll normally put the ore, sulfide ore, into this froth flotation chamber, where we'll have water, and we will be giving an air supply, and with the help of the agitator we can create the bubbles. and if we use a substance like an pine oil, it will be able to create the foam. So as we are pumping in the air and then creating the agitation inside this froth flotation chamber, we will be able to create the foam if we are using an oil like pine oil. And the fact that helps here is the sulfide ore particles, they get wetted by the oil more than the water, whereas the gangue particles, they will be wetted by the water. So since the ore particles are wetted by the oil, they would get carried along with the froth or the foam, and due to the density difference, the froth would be rising to the upper layers, which can be skimmed off and then separated for further steps of the metal extraction. And this is basically the overall process of the froth flotation. We'll take a look at some of the important terms and information related to this froth flotation. So as we just said, we have pine oil or fatty acids or xanthates used to create the foam or froth. They are called as collectors. So collectors will be able to collect the ore particles, and sometimes when the foam is produced, it may not be all that stable to be remaining for the period of operation. So we do use some froth stabilizers like cresols and aniline. And the froth flotation method can also be used if we have the situation where we have to separate two sulfide ores. But here we'll just do a slight modification. We will either adjust the oil to water concentration, or we use a substance called as depressant. So we'll just try to understand what it is with an example. Say for example, we have ore containing zinc sulfide and then lead sulfide. If you use a depressant like sodium cyanide, then it selectively prevents zinc sulfide from coming to the froth, but allows lead sulfide to come with the froth, which means we'll be able to skim off the lead sulfide while the zinc sulfide particles are still remaining inside that a particular froth flotation chamber. So it is preventing zinc sulfide from coming to the froth and allowing the lead sulfide alone. So this is a tool which can be used, the tool of having depressant, if in case we are required to separate two sulfide ores. So this is broadly about the froth flotation, and this is based on, as we discussed, the idea that the ore particles are wetted more by these collectors, and the gangue particles are wetted more by the water. Now the other important enriching step is magnetic separation, also called as electromagnetic separation, since of late in the industry they have been using the electromagnets instead of the permanent magnets. Though in the representation over here we have taken the case of an permanent magnet. If you look at the ores which have magnetic properties like FeCr2O4 chromite, or magnetite, which is a common ore of iron, Fe3O4, or pyrolusite, which is an ore of manganese, all these particles they have magnetic properties, and we can divide the substances into paramagnetic, ferromagnetic. We're talking about the substance having the magnetic properties. The ones that do not have the magnetic properties, they will be called as diamagnetic substances. We'll be able to know about these things in a little bit more detail in a section of solid state topic. But here broadly what happens is we have a feed hopper which will be able to put these powdered ore and gangue particles onto a conveyor belt, and the conveyor belt will be rolling over a wheel which is made up of either a permanent magnetic substance like the rare earth metals, or even here in current age they are using the electromagnets. Now what happens over here is the ore particles which are having magnetic properties, which are marked here in the yellow color, they would get carried with the conveyor belt to a longer distance, since they are attached to the wheel because of the magnetic force, and they would only be falling off at the end of the wheel, since there is no longer the magnetic force over here in this region, so they will be falling over in this part. Whereas the non-magnetic particles, they'll be predominantly falling off due to their kinetic motion. So as they come off the conveyor belt, they'll be having velocities, and we can see typically each of these particles will be falling off at a particular distance. Now, using specific collection chambers, we will be able to collect these particles. And when we talk about the idea that is used over here is if the ore particles have magnetic properties and the gangue particles are non-magnetic, then we will be able to deploy this method to separate the ore particles from the gangue. And it can even be used in vice versa case, which means when the gangue particles are magnetic and the ore particles are non-magnetic, because the idea here is we are trying to separate them. So this method is what we call as the magnetic separation or electromagnetic separation, and this is mainly used for the cases where either the ore particles or the gangue particles have magnetic properties and the other one is non-magnetic. The last and probably one of the important ones, considering that this is an important extraction step also for the noble metals, is the chemical method called as leaching. So the leaching is based on the idea that if we have a suitable reagent, a solvent, and if the ore dissolves in the solvent better than the impurities, then we will be able to take out the ore particles along with the solution and carry out further steps to concentrate the ore. That is the basic idea of leaching. Now, when we look at the leaching of noble metals are leached with a dilute aqueous solution of NaCN, sodium cyanide, or potassium cyanide in the presence of air. Now what happens is the noble metals, whether it is a silver or gold, they would be forming a soluble complex called as, in this case, sodium argentocyanide. If it is a potassium that is used, then it will be forming potassium argentocyanide. So this soluble complex is further made to react with metals like zinc, little bit more reactive metals than the silver and gold, so that we will be able to perform the displacement reaction over there and get back the silver or gold. So this is broadly the step that is involved in the extraction of the gold or silver from their ores. Now the importance of leaching is also there in the extraction of aluminum. So leaching is deployed to enrich alumina from the bauxite. Now other than leaching, there are also a couple of methods, but here when we look at bauxite, along with Al2O3 there will be usually silicon dioxide, iron oxides, titanium oxide as the main impurities. Now when we dissolve powdered solution of the ore with NaOH at a temperature of 473 to 523 and high pressure range of 35 to 36 bar, what we will be able to see is Al2O3 will be leached out as sodium aluminate, and along with Al2O3 there will be also silicon dioxide, which will be able to getting leached as sodium silicate. So the other impurities of oxides of iron, titanium, they will be left behind. So Al2O3 with sodium hydroxide will be able to form a soluble compound, sodium aluminate. Now just keep one thing in mind, along with the sodium aluminate there is also sodium silicate which is being formed. Now we should get rid of this sodium silicate, or rather we should have a method to take the sodium aluminate out. The second step that is involved over here is the formed solution is neutralized by passing CO2 gas. So when we pass CO2 gas, what essentially happens is we'll be able to see that there is an hydrated aluminum oxide that is getting formed, and the hydrated aluminum oxide that is getting formed is made to precipitate by inducing freshly prepared samples of hydrated Al2O3. Basically this is a step where we will induce this precipitation by dropping some freshly prepared hydrated Al2O3, and this step basically separates the sodium aluminate from the sodium silicate. So this formation of hydrated Al2O3 will be able to make sure that we have the Al2O3 hydrated separated out, whereas the sodium silicate is left behind in the solution. And this hydrated Al2O3 will be simply heated at a high temperature range to get back the Al2O3. So these are the broad steps involved in the leaching of alumina from bauxite. And broadly, if you look at the four ore enriching steps that we have seen, each of these cases there is a basic principle which is mostly considering certain properties of the ores, or certain considerations of the metals that are being involved, and the choice and selection of these steps will depend upon these factors. In the subsequent video we'll take a look at the next step involved in the extraction of the metals.